there are some common angles that show up again and again in examples, and it turns out we can actually exactly calculate the trigonometric ratios for those angles. The short version of this is this table here. So down the left-hand side are the common angles. There's 0, pi over 6, pi over 4, pi over 3, and pi over 2, along with their degree equivalents. And the value of all the trigonometric ratios comes from the value of sine and cosine for these angles. We're going to see exactly why these values turn out to be what they are, but the short version is this is what they are. It looks like a lot to remember. First of all, you really only need to know the three main trig functions, sine, cosine, and tangent, because the other three, cosecant, secant, and cotangent, are just the reciprocals of these three. But really, you only need to know sine and cosine, because tangent is just sine over cosine. And really, you only have to remember one of the two columns for sine and cosine, because if you look at these two columns, these numbers are the same, just in the opposite order. So really, there are only a few things to remember here. So let's go through these angles and see why they produce these values. So these angles come up often enough that you do need to know these values of sine and cosine. But you only have to remember one column, and in fact we'll see there's a picture you can draw that makes remembering these values even nicer. So let's see why these values are what you get for sine and cosine for these particular angles. All right, so for each of those angles, we're going to have to draw a triangle that has that angle in it. So first, let's start out with 0 radians, or 0 degrees, same thing. So I guess we'll say theta equals 0. It seems at first like you can't draw a triangle that has a 0 degree angle in it, but in fact you can. It just looks like this. The right angle is hiding down here. The hypotenuse is 1. The angle theta is over here. The adjacent side is 1, and the opposite side is 0. So in this triangle, if you calculate sine of theta, that's going to be sine of 0. You get, right, remember sine is adjacent over hypotenuse, so you get 0 over 1, and that's 0, which is what the table said it should be. And for cosine, you get, I'm sorry, I made a mistake here. For sine, this should be opposite over hypotenuse, and the opposite is 0. There we go. For cosine, adjacent over hypotenuse, and that's 1 over 1, and that's 1. And then tangent is sine over cosine, so 0 over 1 is 0. All right, so that went so well that let's jump down to the end of our list of angles. Let's go with pi over 2, or 90 degrees. This is going to be the same sort of trick, except this time our triangle is just a vertical line segment. So the right angle and theta are both in this at the bottom here. The hypotenuse is 1. The opposite side is 1. And the adjacent side is 0 this time. So sine of pi over 2 is going to be opposite over adjacent, and that's 1 over 1, and that's 1. Cosine of pi over 2 is, I'm sorry, I made a mistake again. Sine is opposite over hypotenuse. Okay. Cosine is adjacent over hypotenuse, and that's 0 over 1, and that's 0. And then tangent is sine over cosine, but that would be 1 over 0, so that's undefined. Okay, those are the easy two. So if we look back at our table, it looks like there are 3 more that we need to do: pi over 6, pi over 4, and pi over 3. We'll see in a minute that actually we can do pi over 6 and pi over 3 with only one picture, so there are 2 more to do. There's the one triangle for pi over 6 and pi over 3, and then there's one for pi over 4. So let's do pi over 4 next. So theta equals pi over 4, or 45 degrees. And if we draw a right triangle with a 45-degree angle in it, like this, the adjacent side is, well, let's call it A. Here we have 45 degrees. There's a right angle right here, but remember, the angles in a triangle have to add up to 180 degrees. We have 45 degrees and another 90 degrees for the right angle, so that means this upper angle also has to be 45 degrees. So this is an isosceles triangle, since it has these 2 angles that are the same. But in an isosceles triangle, the sides opposite the equal angles also have to be equal. So this opposite side actually is the same as the adjacent side. So now we know 2 sides. The adjacent side is A, the opposite side is also A. Well, once you know 2 sides in a right triangle, you can find the length of the third side using the Pythagorean theorem. So now the Pythagorean theorem says the adjacent side squared plus the opposite side squared, but remember the opposite side is the same as the adjacent sides, so that's also A squared, is equal to the hypotenuse squared. On the left-hand side, we can combine these two since they're exactly the same. This is 2a squared equals h squared. And then we can take a square root to find h. Now we would have a plus or minus h here, but h is a length. It has to be positive, so we don't have to acknowledge the negative possibility. And on the left-hand side, this is the square root of 2 times the square root of a squared. So this is the square root of 2 times the square root of a squared is a. Because a is a length, this can't be negative. So this is 2 square root of 2 times a right here. So now that we have a triangle that has the 45-degree angle, a right triangle with the 45-degree angles, now we can evaluate our trig functions. So sine of 45 degrees, or pi over 4, is opposite over hypotenuse. The opposite side has length a. The hypotenuse has length square root of 2 times a. And then we can simplify this. So 1 over square root of 2. Some people don't like to have a square root in the denominator. Personally, I don't have a problem with it, but if you don't like having the square root in the denominator, you can multiply the numerator and denominator of this by the square root of 2, and you get the square root of 2 over 2. Okay, for the cosine of pi over 4, well, because of the symmetry of the triangle, you can tell it's going to be the same thing. But just to write it out, cosine is adjacent, which is a, over the hypotenuse, which is square root of 2 times a. And yeah, that's going to be exactly the same, so we can jump to the end. It's 1 over root 2, or root 2 over 2. And then tangent of pi over 4. Well, tangent is sine over cosine, but sine and cosine are the same, so when you divide a number by itself, you get 1. All right. So now we only have one triangle left. Looking back at our table, we need to draw a triangle that has a 30-degree angle. Sorry, a right triangle that has a 30-degree angle. So let's do that over here. So theta equals 30 degrees, or 30 degrees is also known as pi over 6 radians. So 30 degrees looks about like that. And the right angle is right here. And let's call the opposite side O. Now, if you do the arithmetic to find the missing angle, it turns out it's 60 degrees. So using this triangle, we can find sine and cosine of 30 and 60. So this is why we only need this one triangle for both of those angles. But it's unlike with the last case, with the last 45-degree triangle, there's no obvious symmetry that makes things easy to work out here. But one thing you can do is, if you draw another copy of the triangle down here, so it's 60 degrees right there and 30 degrees right here, that means that this right-hand dotted length must also be O. Well, now we have a triangle with three 60-degree angles in it. If you look at this big triangle here in blue, the top angle is 60, the bottom angle is 60, and the left-hand angle is two copies of 30 degrees, in other words, also 60. So this triangle is equilateral because all of the angles are the same. When all of the angles are the same, that means all the sides are the same as well. So how long are the sides? Well, the right-hand side is two copies of O, so that's 2O. So that means all of the sides in this big blue triangle are 2O. Notice that this top left-hand side, that's the hypotenuse of our original triangle. So now we know the hypotenuse. It's 2 times O. And we know the opposite side, because we called that O. So we can use the Pythagorean theorem to find the remaining side, which is the adjacent side. So the Pythagorean theorem says that the adjacent side squared plus the opposite side squared is equal to the hypotenuse squared, and the hypotenuse is 2 times O. So this is A squared plus O squared equals 2O squared is 4 times O squared. Then we can subtract O squared from both sides. Remember, we're trying to find A. So this gives us A squared equals 3 times O squared. And then we can take a square root to find the adjacent side. So the adjacent side is the square root of 3O squared. And we don't have to worry about a negative possibility because A is a side length, so it has to be positive. And this is the square root of 3 times O. All right, so now we know all of the sides in this triangle. We can work out the trigonometric ratios. So sine of 30 degrees is the opposite side, O, over the side adjacent to the 30-degree angle, which is A, and that's square root of 3. No, this isn't right. It's the opposite over the hypotenuse. So that's O divided by 2O, and that's a half, which is what the table said, I hope, so that's good. Cosine of 30 degrees is the adjacent side divided by the hypotenuse. The adjacent side is the square root of 3 times O. The hypotenuse is 2 times O. And so cosine of 30 degrees is the square root of 3 over 2, just like it was supposed to be. Finally, for tangent of 30 degrees, it's sine over cosine, or you can do opposite over adjacent. And the adjacent side was square root of 3 times O. And that's 1 over root 3, just like it was supposed to be. All right, now what about the 60-degree angle? So what about sine of 60 degrees? Well, if you look up at this diagram, sine should be opposite over hypotenuse, but remember, opposite means opposite the angle you're talking about. So the side opposite the 60-degree angle is the red side, which is square root of 3 times O. So square root of 3 times O divided by the hypotenuse, and the hypotenuse is still 2 times O. 2O, and that gives us, once you simplify the O's, you get square root of 3 over 2. Cosine of 60 degrees is, again, we have to look at the side adjacent to the 60-degree angle, which is confusingly called O in this diagram, and the hypotenuse, which is 2O. So this is O divided by 2O, and then simplify the O's, you get a half. And tangent of 60 degrees is the side opposite, which is root 3O, divided by the side adjacent, which is O. So root 3O divided by O, and then simplify. So this is the square root of 3. All right, so finally, we've worked out all of the trigonometric ratios in this table. So again, to remember this table, really you only have to remember the column for sine. It turns out that most angles don't have nice sines or cosines. These are some of the few angles that have sines and cosines that are sort of easy to remember. We'll see later in the quarter that there are some other angles that you can calculate exactly without just approximating using a calculator, but those are sort of few and far between.